written. Where is the mouse? Yeah, this talk will be based on this paper written in collaboration with Peter Kravchuk and Colin Mazak. Both of them are in IS, Princeton. So as the title suggests that, so we all know the story about conformal bootstrap. Conformal bootstrap is the main idea of conformal bootstrap is to use the crossing symmetry to put constraint on the conformal data of conformal field theory like OP coefficients or spectrum of operators and so on. And so here we will see that the same kind of ideas and same kind of notion of OPs, the notion of spectrum of operators, everything will appear in a completely different context, in the context of automorphic spectra and automorphic forms, which are nothing but a generalization of periodic function defined on some group manifold. So we will see that in all practical purpose in this talk by automorphic spectra, I mean we will be meaning the Laplacian spectra defined on some hyperbolic, compact hyperbolic manifold. And it will turn out that these Laplacian eigenfunctions defined on compact hyperbolic manifold can be lifted onto some group manifold. And lo and behold, the group manifold that we will be focusing on is precisely the conformal group manifold. So as the talk progresses, and my job is to explain this precise connection between the appearance between this conformal bootstrap and the automorphic spectra, and to be more precise, how the conformal group appears in the story of automorphic spectra, and how we can use the ideas from the conformal bootstrap to constrain the Laplacian spectrum on some hyperbolic manifold. And please feel free to ask questions at any point if something is unclear. And with that, I will move to my next slide. Somehow it's not working.
I think you have to click on the presentation.
Yeah, it's.
Now it should work.
I guess probably this one.
Oh, okay.
I think it was not.
It's working.
Yeah, it's sure. Yeah. Yeah, it's working. So as I was saying, so there you can see two diamonds here. In the green diamond, we have the ideas of conformal bootstrap, which you do in d-1 dimension. And on the other side, you have the spectral geometry of d-dimensional hyperbolic manifold. And our objective is to show the remarkably precise connection between these two things. And at the end of the day, they will be basically guided by this Euclidean conformal group to be very specific, the connected component of SO1, T. On this side, this is basically a conformal symmetry. So you have translation symmetry, rotation and scaling, and special conformal transformation, which acts on d-1 dimension. And on this side, this group appears as the isometric group of the hyperbolic manifold with constant curvature. So what happens that this group acts naturally on the hyperbolic manifold and takes you from one point to the other point. And under this action of group, the metric on this manifold, which is the hyperbolic metric, remains invariant. So this is an isometry. And in both cases, the representation of SO1, D will play a crucial role. And we will see in this side, we have bounds on the operator spectrum. On this side, we will have bounds on the Laplacian spectrum. So the next point is, why do we care about this problem?
Question.
Yeah.
Is there a special meaning of zero there, or it's just the
Yes.
usual SO1, D that we know?
So this zero basically means we are looking at the connected component of SO1, D. So that's the notation.
Is
Sometimes
there
we will write it as a plus also.
there a holographic picture here underlying this or not?
No, not really.
Okay.
Like in this, so at the end of the day, you will see that there is so this thing can be thought of as a toy model of a CFT, but it has it's a simpler version of a CFT. So there are a lot of similarities, but in some sense, it's also a bit different, not exactly same. This will be clear as the talk goes on. So the next point is, why do we care about this problem? And the answer really depends on like in which problem you are interested in, whether you're coming from a physics background or a math background. So from the physics perspective, I guess the main motivation behind studying this problem is that we are able to make this connection precise. So we can think of this thing as the thing appearing on the red diamond as a toy model for a CFT. And probably there is a hope that this toy model will help us to learn something about the chaotic CFTs. For example, it is a very hard problem to analyze chaos in a conformal field theory. And to show you the hardness, I can tell you this, that for example, in 2D conformal field theory, there is no known example of a modular invariant partition function which shows chaos in their spectrum. But people believe from the holographic side, because it's a dual of a black hole and so on, ADS3 black hole, that there should be chaotic CFTs which have chaos in their spectrum.
Is there a very concise way of saying what is chaotic spectrum in the nutshell?
Yeah, so I guess one definition would be that you would expect the random matrix like not Poisson distribution in the eigenvalue of the Hamiltonian. Rather, you will have random matrix like behavior. But then it's very hard to imagine a modular invariant partition function where you do a Q expansion and all the deltas behave like RMT, like random matrix. And yeah. And so, but on the other hand, we know the hyperbolic manifolds are classically chaotic because all the geodesics diverge. And not only that, there is a notion of quantum chaos on this hyperbolic manifold in the sense the Laplacian spectra on compact hyperbolic manifold show something called arithmetic chaos, which is defined by Peter Sarnak and other mathematicians. So one might hope that this will teach us. So if we can bound the spectra on this side, maybe it will teach us something about chaos on the hyperbolic manifold, and it will give us some insight about how chaos occurs in the actual CFT. So you can think of it, this is a long-term dream or a long-term goal of thinking about this problem. And this is how we came to think about this.
Are these finite volume hyperbolic manifolds?
Yeah, they are finite volume and compact. So the Laplacian spectrum is discrete. Yeah.
So that SO1D is acting only locally.
Yeah, yeah. And then from the maths point of view, there are a lot of unproven conjectures in math literature about the Laplacian spectrum on compact hyperbolic manifold. For example, there's a conjecture, so you can think about all the genus 2 surfaces, which has finite volume. And it is known the most symmetric genus 2 surface is something called Bolza surface. And there is a conjecture that the Bolza surface maximizes the gap among all the genus 2 surfaces. The gap in the sense that it has the highest lambda 1, the first non-trivial eigenvalue of the Laplacian. In a similar way, in genus 3, there is a conjecture that the most symmetric genus 3 surface, which is the Klein quartic, maximizes the gap. And all these conjectures are unproven. And this bootstrap basically gives you a tool to attack these problems, because bootstrap at the end of the day produces an upper bound on this lambda 1. And once you have an upper bound, and if you can show that this upper bound is saturated by your known examples of Bolza surface or Klein quartic, you are done. You can basically prove this. And you will see that our bounds are very close to saturation. So in some way, we are giving more evidence to these conjectures. And finally, if you are interested in de-Sitter, then recently there have been developments in the de-Sitter bootstrap where people look at some correlators, cosmological correlators on a late time slice. And this correlators transforms under this group SO1, D. And people have been trying to bootstrap those correlators using some crossing symmetry involving this group. So there is a mathematical kind of, so at the end of the day, we'll be writing some crossing equation here, which is some consistency conditions. And those consistency conditions, mathematically speaking, is also applicable in this de-Sitter setup. So there could be some, so all the technology we develop should also be applicable in this scenario. But for the rest of the talk, I will only be talking about hyperbolic manifold, and to be very specific, I will be talking about two-dimensional hyperbolic manifold, which are basically hyperbolic surface. And if I should be very precise, I should be talking about orbifolds. So manifold is an orbifold without any orbifold singularities. So whenever I say hyperbolic surface, I mean hyperbolic orbifolds and smooth hyperbolic manifolds. Moving on. So let us start with spectral geometry of hyperbolic surface. So the most important thing is that in any two dimensions, we can think about the upper half plane as a model for hyperdimensional. And you can put the hyperbolic metric on this upper half plane H. And then there is a theorem which tells you that then the point is there is an orientation preserving isometric group of this upper half plane, which is precisely SO1, 2, it's also known as PSL2R. So this PSL2R acts on the upper half plane. If you denote the upper half plane coordinate as Z variable, then it precisely acts as a Mobius transformation on the upper half plane. So you can go from one point to other point by using this PSL2R. And now you can consider some discrete subgroup of PSL2R, which I call gamma here. And the elements of gamma can be of three kinds. Either it can, so PSL2R is like a conformal group acting on the two dimension. So basically it has translation, rotation, and scaling. So all the elements of gamma can be classified in three groups. If they are called parabolic, if they are conjugate to translation, they are called elliptic if they are conjugate to rotation, and if they are conjugate to scaling, they are called hyperbolic. So we have three kinds of elements in gamma or in PSL2R, which are parabolic, elliptic, and hyperbolic. Now, if we demand that if I choose a discrete subgroup of PSL2R, which is gamma, which does not have any parabolic element, and after picking this group, if I quotient the upper half plane by this group, gamma, which means basically you take the upper half plane, you pick a point, you act with gamma, you land up with a different point, and then you identify those 2 points, which are related by gamma. If you do this identification, and if you implement this condition that gamma is a discrete subgroup and it does not have any parabolic element, which means does not have any elements which are conjugate to translation, then you land up with a compact hyperbolic surface. So the upshot is that any compact hyperbolic surface can be given a group theoretic description where you take the upper half plane and quotient it by some gamma, where gamma is a discrete subgroup of PSL2R, and it does not have any parabolic element. And in math literature, this gamma is called Fuchsian group. And this is a very standard construction. And with this construction, we will, so the reason I am telling you this, because we are going to define the Laplacian on this compact hyperbolic surface, like on this group manifold, on this H quotient out by gamma thing.
Do you get Platonic solids in this way by any chance?
The hyperbolic version of those things do appear. Like you can think of hyperbolic triangles and so on. Like by Platonic solids, do you
Imagine this kind of how can I say this? A surface with edge, corners and edges, like.
Oh, I see. Yeah, I guess hyperbolic triangles would have like 3 conical singularities, and it will be like this. But I guess at the end of the day, it's a 2D surface.
Tetrahedron, for example.
Oh, I see. So no, to getting the tetrahedron and those versions, you have to consider 3D manifolds.
Oh,
so these are all 2D things I am talking about.
On the surface, I mean, surface of it.
Oh, you mean the surface of a tetrahedron?
Yes. Is it included in your scheme?
Yeah. As long as you can put the hyperbolic metric on it and maintain a constant sectional curvature, is all included. Yeah. So the only requirement is it has to have compact. It has to be compact, and which also means it has finite volume.
Just one last question.
Yes, sure.
There's also something called teardrop. Are you familiar?
I see what. Yeah. So when I am saying orbifolds, I mean the good orbifolds, which has a covering of a manifold, and those teardrops are not allowed.
Yes, indeed. Okay, thank you.
Yeah, exactly. And because those are not allowed, this statement is true. I can always write it down in this nice quotient form. As I was saying, you define the Laplacian on the upper half plane, which is given by this operator, which is self-adjoint. So on the full upper half plane, this operator has a continuous spectrum, so everything is allowed. Every possible eigenvalue is allowed. But then we are not looking at the Laplacian on the upper half plane, rather we are looking at the Laplacian on this compact surface. So how do you think about the Laplacian on the compact surface? The idea is same, like you construct this operator, you consider the same operators, but then you consider the eigenfunctions because your group PSL2R and hence the group gamma acts on your functions. It acts on f of x and it goes into f of gamma inverse x. So basically you look for eigenvalues which corresponds to gamma invariant eigenfunctions. So roughly speaking, it's like you can think of an analogous situation on a real line where instead of, suppose you are looking at solving Laplacian on a real line, then everything is allowed. But then you put the condition that you want to solve it on S1. So you impose this periodic boundary condition. And the generalization of the periodic boundary condition is precisely this, is that you do not pick everything, you only pick those which are invariant under this subgroup gamma. And because the gamma does not have any parabolic elements and the surface is compact, this immediately tells you the spectrum is discrete. There is a minimum, which is the eigenvalue 0, which is the constant function. And the constant function is allowed because it's compact and has a finite volume. So it's L2 integrable. So the spectrum starts with 0. And then there are some discrete points, lambda 1, lambda 2, and so on. And concretely, our goal is to put bound on this lambda 1. So in the CFT literature, when we use crossing, we put bounds on the first non-trivial non-vacuum state. And here we are putting bounds on the first non-trivial Laplacian eigenvalue on any compact surface, compact hyperbolic surface, which are described by this H/gamma. So now at this point,
It is mathematically interesting question,
Yeah.
but physics-wise, where do we need that information in a physics problem typically?
typically, as I was saying, the main motivation is to understand chaos. So at the end of the day, so I guess the main question I have in mind is that there is a notion of arithmetic chaos in the hyperbolic surface, and there is no notion of arithmetic chaos in the CFT. So there is a high chance that the chaos we expect in the CFT is actually arithmetic chaos, not the RMT-like chaos. So there can be some grading and things like that. So the long-term hope in the physics line is that to understand those things better.
Okay. And gamma will play a crucial role, obviously, right?
Yeah.
All depends on gamma.
So yeah, right. So you can think of this. So roughly the analogy is this gamma slash this H/gamma. It will be the analog of field configurations in some sense, the space of field configuration. And you will see the notion of OP and everything appears in this setup also. So this is a nice, this will give us a nice handle. And of course, from the math perspective, people are really interested in the Laplacian eigenvalues on the hyperbolic spectrum, like connection to number theory and so on. So. Say that again.
So which way does it go? Are you going to use the results from mathematicians?
No. So
Or are you going to compute the eigenvalues for them?
So we are going to put bounds on this Laplacian eigenvalues. So it would be a new result for them. So there are conjectures about these eigenvalues that suppose there is a conjecture that genus 2 Bolza surface maximizes the gap. And the only way you can prove the conjecture is you put an upper bound on all possible genus 2 surfaces and then show that your upper bound is saturated by the actual Bolza surface. So this kind of thing, there are lots of conjectures like this in the math literature, and our technique will be a nice technique to tackle those problems, attack those problems. And it's kind of, I kind of find it funny that some mathematicians have not explored this kind of techniques before. So it's a completely new thing for them. That's the fact that you can extract such a detailed information about the spectrum. So the first point is, why do we expect a bound even? Like in the CFT literature, in the CFT we expect a bound because there is a notion of operator product expansion, and we know the operator product expansion is associative. So it, like if you take operator product of 1, 2, and 3, it doesn't really matter whether you do 1 and 2 first. and then with 3, or 2 or 3 first, and then with 1. So here also on the manifold, there is a notion of associativity, which is basically the associativity of multiplication of 2 functions. So this is how we can see that why do we expect a bound. So for example, you take this Fi, Fj, Fk. So consider these 3 are Laplacian eigenfunctions which are properly normalized and orthogonal to each other. Then you can multiply them together like Fi, Fj, Fk pointwise, and then you can integrate over the whole manifold. And this is what defines something analogous to 3-point functions, which I denote as Cij. And another way of saying the same thing is that if you multiply Fi and Fj together, then you can again expand it in the basis of Laplacian eigenfunctions, and the coefficients that will appear in this expansion is precisely Cij. So keep this in mind, and then you will immediately see why there should be a bound or some consistency conditions. So moving ahead, you can define a 4-point functions which are like Fi, Fj, Fj. Again, this is defined in a standard way. You take 4 functions, multiply them pointwise, and integrate over the whole manifold. Now you can do now to evaluate this integral. You can do it 2 ways. First, you take Fi, the first one, and the third one, Fi and Fj. You use this fact that you can expand it in the eigenbasis, so you get a sum Cij, Fk. And then you exchange the sum and the integral. So this goes out, and then you have another integral which is Fk, Fi, Fj. And once you integrate over these 3 things, you get another 3-point coefficients, which is again Cij. So this whole thing can be written down as a sum over Cij square. But one can come up with a different method where instead of going for first and the third, you go with first and the second. So you contract Fi and Fi. So you get something like Ciik, Fk, Fj, Fj, and then you integrate over the manifold. So you get another 3-point coefficient, which is basically Cjjk. And now the point is, it doesn't really matter how you evaluate this integral, both of the channels should give you the same result. And that immediately tells you that there is a constraint or there is a crossing equation which looks like this. And the whole point is you can take various combination of these crossing equations, like you can take derivatives and write down many more equations like this. And once you have a set of consistency equations, you can put it on the SDPP and look for linear functionals and produce some bounds. So this is how Hinterbichler and Bonifacio, like a couple of years back, came up with bounds for something called Einsteinian manifold. But the whole point is, at this point, you can see that basically you take 4 functions, you do it a basis expansion in a brute force way in 2 different ways, and you get some crossing equation. But the whole group theory picture is missing. Like at this point, if you ask me what are the operators, what is my Hilbert space, how the PSL in this calculation there is no notion of PSL2 or some conformal group acting. So
Cijk constants?
Yes, they are constants.
And when you take product of Fi with Fj, is it really just commutative pointwise multiplication of functions?
Yeah.
There are no hidden operations. You haven't told us about. Okay.
No, these are the simple.
Just multiplying two functions.
Exactly.
Can you remind us why Fi, Fj, Cij, Kfk? What's the reason behind it?
What's what?
So you have Fi, Fj.
Yeah.
Integral is Cij, Kfk.
Yeah.
And Cij, K are constants, so that's a deal. So why we have this?
Why do we have a constraint from?
Right.
It's integrated the functions, right? So what else can you get?
Without integrating, they are constants.
Yeah.
So why is
So that is just Fi Fj is a function, and then you are expanding it in the basis of eigenfunctions. So that's just
okay?
that.
So I missed the point. Okay. Yeah, I'm sorry. Okay.
Good. Yeah. Please feel free to stop me because I tend to go fast and
I thought you were.
yeah. But the whole point is this is a very simple looking calculation, but this calculation hides a lot of beautiful structure that underlies, because nowhere in this calculation there is a mention of conformal group. Nowhere we have the notion of operators or Hilbert space and so on. So by making so in what follows, we will making the connection with the actual conformal field theory much more precise. So as I was mentioning briefly before, so the modern incarnation of conformal bootstrap is study of 4-point correlator, and there is a notion of OP and then associativity of OP, which leads to symmetry. So our job will be to actually, given a hyperbolic manifold, our job will be to actually construct the operators, identify the Hilbert space, precisely describe how the conformal group acts on those states, and then define the notion of OP, and then define the associativity of OP, and land up with an equation like this. And from this, everything will follow. All the equations that I showed you before in a brute force way will follow just one line once you make that connection. And before going into details, I just want to show you what kind of results you get by doing this procedure. So this is a slide of results. So the theorems we prove, and by theorems I mean really theorems in all math rigorous standard, that for any hyperbolic orbifold, the lambda 1, the first non-trivial eigenvalue, has to satisfy this bound, which is for 4.8883537. Then any hyperbolic orbifold of genus 2 must satisfy this bound, which is again 3.838897641. And any hyperbolic orbifold of genus 3 must satisfy this bound, which is again given by 2.7 some numbers.
They are irrational numbers, right? I mean, are those rational or irrational numbers that
so the bounds we obtain, they are rational numbers, and they are exact bounds. It's possible that if you put in more equations, you can improve those bounds, but we believe these bounds are like, except for the last digit, all the digits are converged. So you can only improve the last digit by putting in more equations.
Normalize the volume somehow.
Yeah, the Ricci scalar. But I guess the whole point is that when you, at the end of the day, we'll recast the whole problem into a group theory problem, then everything is normalized. Then the normalization comes in the definition of the OP coefficients. Because when you when we define the OP coefficients in CFT, we always use a normalization that when O and O dagger fuse, we get identity with a one coefficient. So that's where the normalization of the volume will be hidden. Yeah. Oh, it basically boils down to that, like how much precise we want to be. Like here we ran the. I can tell you that why, like the point is that yeah, there is no obvious reason why we did that. The one reason is because of these examples we have. So for the first one there is a notion of orbifold with smallest volume, and there is a description of that orbifold, and you can numerically calculate the Laplacian eigenvalue on this smallest volume surface, and the value you get by computing numerically is exactly this 44.8883537.
It's an exact number, that's not correct.
Yeah, but the point is that like this numerical value is also known up to this point. So presumably the actual value is an irrational number. Like you only, so when I am saying nearly saturating, I mean that our bound matches with the known value up to some decimal places, because the values that is known from doing numerics on the Laplace on that particular surface is also known like up to some decimal places, not exactly.
What would Ramanujan say to this if he saw these numbers?
Maybe he will come up with something and will prove the results. Yeah, who knows? Yeah. And then again, I was saying for genus 2, there is a Bolza surface which has a value, you can see 3 points. So this is again the numerics, like on this particular surface, 3.838887258, and you can see here 3.83889. So our bound matches up to 4 decimal places. And again, our bound can be improved, and if we use more and more correlators, it will presumably converge to this value. But again, this value is also like, you should not treat this as an exact rational number, because there are other digits which are omitted from here. Like people only know up to these decimal places. In the same way, in genus 3 Klein quartic, people know up to 4 decimal places, which is 2.6779, and our bound is 2.6784. So you can see these bounds are very nearly saturating, which is an amazing result from the perspective of the conformal field theory, because in the conformal field theory, people have done like for the Ising model to get the island and to get a match, people have to work like 7-8 years to get that precision. But here somehow things are very like in this toy model, things are very friendly to a bootstrapper. And the second thing is that all these bounds beat the base known previous bounds. For example, the base known previous bound for genus 2 is Yang-Yao bound, which is the bound is 4. We beat that bound. And for genus 3, the best known bound is only came last year by Ross, a mathematician in 2020, which was 2.7085. And we also beat this bound by a little bit, like we have 2.67. Okay.
How do you calculate the genus, by the way, given your definition of the hyperbolic manifolds?
Yeah, so you will see that thing, how the genus information comes in. Yeah, it's the magic of Riemann rock and some connection between the representation theory of PSL2R and these structures. Yeah.
And to decide the chaotic behavior, you'll have to find other arguments.
Yeah.
You know how to do.
Yeah, so there is a way to extract the spectrum. So on the very last slide, I hope I will get to that very last slide. You will see that where we can extract the spectrum, at least for this case, where the smallest volume case. Great. So now I will give you some flavor of what kind of surfaces we deal with and what kind of groups and how the information about the genus and everything comes in. So the simplest possible hyperbolic surface is the triangle surface. So we consider the upper half plane. This is the upper half plane. And we know the geodesics are like semicircles. So you draw these 3 geodesics and they cut in 3 points ABC. So this ABC forms a triangle. And then if you pick your angles alpha, beta, gamma in a way so that they can be written down as pi over some integer, K1, K2, K3, then you can consider reflections around these 3 geodesics, like 3 parts of geodesic AC, AB, and BC. And these reflections forms a group, and it's a discrete group of the SL2R. And this group is called triangle group. And then you can consider another subgroup of this triangle group, which is called Von Dyck group, which is basically the orientation preserving index 2 subgroup, which basically means that here you have, so you can always pair of the reflections, take 2 reflections. And then if you consider a group which are always constructed by even number of reflections, then you do not change the orientation. So you can consider an orientation preserving subgroup of this triangle group, which is called Von Dyck group. And the idea is that if you consider the upper half plane and quotient it by this Von Dyck group, you get an object which looks like this triangle ABC, where you fold the triangle along the geodesic and you get a surface with 3 orbifold points, and everywhere there is a hyperbolic metric. And these 3 orbifold points have the orbifold order given by this K1, K2, and K3. And there is something called signature of gamma, which basically encodes this information that in which genus you are. So this is a genus 0 surface, the surface I just described. And you have these 3 orbifold points, K1, K2, and K3, and their order are K1, K2, K3. So this signature of gamma encodes some amount of geometric information about the surface, like what genus you are and how many things are. And the signature of gamma will play a crucial role in our bootstrap. And that is how the information will go in, that which genus are you looking at, what kind of orbifold points we're looking at, and so on.
How does the reflection act on a given point geometrically?
So geometrically, you have to just take the surface and just, it's like a light reflection, like
Around what axis?
around this line AC. So you take a point and you reflect it, take a tangent and like it's a reflection on a curved surface, like light reflection. And you need these conditions pi over K1, pi over K2, like this K1, K2, K3 needs to be integer because you want to close it onto itself. Otherwise, it cannot tile the whole surface. So you need to have a discrete group, that's why. And then as I was saying, the orbifold with smallest volume, the surface that appears in the previous slide, is given by the signature, which is genus 0, and there are 3 orbifold points given by 2, 3, and 7. And there is a math proof which shows that this is the orbifold with the smallest volume. The second smallest one corresponds to 0, 2, 3, 8. And I am mentioning these two because they will appear again and again in various contexts where our bound will be saturated by surfaces given by this gamma. Then for genus 2, I talked about Bolza surface. So this is a picture taken from Wikipedia. And so you take 96 of these 2, 3, 8 triangles and glue them together properly so there are no orbifold singularities. So this upliftment gives you the most symmetric genus 2 surface, which is the Bolza surface, which looks like this. And in the same way, in the genus 3, you can take 336 of these 2, 3, 7 triangles and glue them together properly so that there is no orbifold singularity anymore. And this covering is the most symmetric one. And they are named after Klein. This is called Klein quartic surface. So in most of the occasions, the bound we put are actually saturated either by these 2, 3, 7 triangles or 2, 3, 8 triangles, or they are coverings which have a smooth coverings, which are genus 2 Bolza or genus 3 Klein.
What do the integers around the boundary mean?
Oh,
They're identified.
yeah. So 1 is identified with 1, 2 is identified with 2, and so on. Yeah. And these small things are these triangles, this 2, 3, 7. So if you count everything, there are, I haven't counted, but you can. So the nicest way to check is that you know the area of the 2, 3, 7 triangle, you know the area of the genus 3 surface by remainder like this theorem, which tells you the volume. And then you divide and you see there are 336 of them. That's the quickest way to check. Okay, good. Is there any question?
So you haven't told us yet how to compute the genus, right?
No, I have. So yeah, I haven't told you yet. So you will later see how the information about genus comes in. I should probably hurry a bit, but so now I'll come to the main thing, like how do you bootstrap the hyperbolic surface? How do you construct the Hilbert space, and so on. So the first guess would be that the first guess for the Hilbert space would be you consider all L2 integrable functions on the surface and you declare it to be Hilbert space. This is nice, and all this of course forms a Hilbert space because this is L2 integrable. But the problem is that this is not a representation of the group conformal group PSL2R, because the PSL2R, the complexified PSL2R algebra has some generators, and these generators acts on these functions and takes you away from this space. Because, for example, if you take derivatives then of these functions, they do not belong to the L2 space because they become forms basically. So you have to enlarge this Hilbert space so that it becomes a representation of PSL2R. So to do this, you realize the following thing. So you consider this upper half plane H, and this is very important. This upper half plane H can be thought of as a quotient of G by K, where G is the group PSL2R and K is the stabilizer group of a point, which is basically rotation modulo this plus minus identity. Now, any functions you define on this thing can be uplifted on this function defined on this G. And then you can define an enlarged space, which is basically all the L2 integrable functions defined on G/gamma. So now the idea is that I'll claim that this thing is a representation of the group PSL2R very naturally. So pictorially, this is what happened. You have the Riemann surface. You have the surface, the hyperbolic surface, which is X. So initially you have functions living on the surface, but then you enlarge your Hilbert space, enlarge your form space, and then you have this extra circle, which is S1. So you have a total space, and now all your functions live on parameterized by 3 coordinates, which is X and Y, which are the coordinates on the surface, and there is a third coordinate theta, which lives on the circle. And all these functions belong to L2 gamma G slash gamma, so the bigger Hilbert space. So now you can, like as I was promising, that this is a Hilbert space, so you can define an inner product. And the way to define the inner product, you take two functions, you complex conjugate one of them, multiply them together, and now integrate over the bigger space, which is G slash gamma. And the way you see that this is a representation of the actual group PSL2R, you basically define your composition law, which is take a group element G tilde, it acts on your function F, and it is a different function, which is equal to the original function F evaluated at G tilde. And then you can check that this composition law like satisfy all the group composition law, and this makes the functional space, the Hilbert space, into a representation of the PSL2R. So now we have the representation of the PSL2R.
Can you stay close to the microphone there, because I think people online are having trouble if you go away from
Okay.
Yeah,
Thanks.
that's fine.
Okay.
Can you clarify again? So why could you not do this with just gamma slash H,
Oh,
but you can do it now with gamma slash G? What
Because-
changes?
yeah, because the point is that there are, like, you can wait for a slide. It will be clear in the next slide.
Okay.
So the point is, because we know how the G tilde acts on these functions F, you also know how the algebra acts on this function. So the PSL2R, the algebra has a three generators, L1, L-1, and L0. And just from this, you can write the following thing, which are basically three differential operators, L1, L-1. And I have not written the L0, but L0 is basically del L theta, which generates the S1. Now here's so suppose you take a functions which are function of X and Y, and you act with L1, then you see that there is another theta variable that comes along. So the whole point is there are differential forms which lives on the surface, and those differential forms are not included in the L2 space of gamma slash H. And the way to include those differential forms inside your analysis, you uplift your space, so the differential forms become an actual function on the bigger space. So you consider all the functions in the bigger space, and on the base space, they become the actual function or the differential form, or like holomorphic differential form or anti-holomorphic differential form. So you treat functions and forms, everything together, by going to the bigger space. And then there is a Casimir. The Casimir is given by this differential operator. And now this Casimir will play again a crucial role, as we will see in the next slide. So, okay, not the next slide. So in the next slide, we define so before that, I need to define the correlators. So earlier we took the functions defined on the orbifold and multiply them together. But now I take the functions on this bigger thing, which is G slash gamma. Again, I pointwise multiply them and integrate over this bigger space, and that defines my correlator. Now there are some crucial observations we make. That the first of all, if my function F is the theta independent, which is the S1 independent, they naturally descends to a function on the surface, and then these two definition matches, because earlier I defined this correlator as an integral over gamma slash H, and here I defined the correlator as G slash gamma. And because this extra direction is a finite compact direction, we basically this boils down to this. And the next important observation is that I write down the Casimir, which acts on this function F. But now if F is theta independent, then this term drops out. And lo and behold, this is precisely the Laplacian operator acting on this function F. So this is how you first make the connection with the group theory object, which is the Casimir, with the Laplacian. So if you make some observation or make some bounds on the Casimir by doing group theory, you actually are making some observation or making some bound on the spectrum of the Laplacian. So this is the first connection. Then as I was telling Anindo, the idea is there is a extra S1 circle. So basically this whole Hilbert space is graded. You can grade along the according to the eigenvalues of L0. So you can write it as a sum over Vn. And the idea is the Vn's are related to the n forms living on the surface. And as I was saying, the main upshot is that by considering this bigger space, you are considering all the differential forms, functions, everything in the same go. And then let us focus on the forms, because they will play again a crucial role. So the way you relate the forms and the functions is by following way. So you take a function from this bigger space, which is f x y theta. You parameterize it in this fashion, is y to the power n exponential I n theta and h x y. And the fact that your function f is gamma invariant on the bigger space, like you can do some calculation which is like tedious, but you can do it, and at the end of the day you will show that your function h exactly behaves like a modular form living on the surface. Like under the action of gamma, they transform with these prefactors, which are precisely the prefactors of a modular form. So now you make the connection that the stuff that is living inside Vn's, which are the other objects which was not in V0, are related to the modular forms. And then on top of that, you make another crucial observation that, like, you know the action of L1 and L-1 on this function. If this L1 and L-1, this function annihilates this L1 and L-1, they annihilate the function f, then in terms of surface, it precisely the statement of function h being holomorphic or anti-holomorphic. So now we have some connections with, so basically we have a Hilbert space, we have three different objects inside the Hilbert space, and they are related to three different things living on the surface. So next, we ask the question group theorists will always ask. We take the Hilbert space L2 gamma slash G, and the next obvious question is, how do you decompose into irreps of PSL2R? And the irreps of PSL2R comes in a different kinds. The first one is the trivial representation, which is basically the constant function. Then you have this discrete holomorphic and the discrete anti-holomorphic representation, which are basically lowest weight and highest weight representation. They are defined by these two conditions. And just in the previous slide, I told you that these two conditions means that you are dealing with holomorphic forms, holomorphic differential forms, and anti-holomorphic differential forms. And finally, you have this C lambda k, which is called continuous representation of PSL2R. And again, you can show that this thing is related to the Laplacian eigenfunction, and the Casimir corresponding to this is related to the eigenvalue. So it's a group theory problem to do this decomposition and figure out the multiplicity of these guys.
The ones in the middle, discrete representation.
Yeah. And a sub problem of this decomposition is to figure out what kinds of lambda k can appear. And this is precisely what we want. We want to put a bound on possible values of lambda k. So we have turned our problem into a complete group theory problem.
Why not the discrete ones also? They may have conditions, right?
Yes, now I come back to your question, how the information about genus comes in. So this is how it comes in. Let me explain. So the thing is that these are, I told you, these are related to the holomorphic differential forms and the anti-holomorphic differential forms. But now we have Riemann and Roch, they wrote down a special theorem which tells you that given a signature of gamma, given the genus, you know exactly how many differential forms, holomorphic differential forms of a given weight are present on the surface. So in this decomposition, once you know the information about gamma, once you know the information about genus or how many orbifold singularities are there, you know exactly how many are sitting there in this decomposition. So you can input that information in your setup and gain some information about this thing. And you already know, so this C is known because it's a unique identity. There is a one constant function. This thing is also known if you give in the information about gamma, and our object is to figure out some information about C lambda. And that's how the information about the gamma goes in, the genus goes in. Okay. So again, these are now the point is that earlier I talked about the associativity of the functional multiplication on the surface. Now we can talk about the associativity of functional multiplication on the bigger space. So you take two functions f1 and f2 and multiply them together, and then you can project onto different irreps. So this is the projection onto identity. This is a projection onto discrete holomorphic and a discrete anti-holomorphic. And this is a projection onto continuous series. And then there is a notion of associativity, which tells you that these two things are same. And this is what would constrain on this possible breakout of F1, F2 in different irreps. So to do that more nicely, you do the following thing. So this slide is a bit technical, but all I want, so basically you take the lowest weight state and the highest weight state in the discrete holomorphic and anti-holomorphic. You know how these generators acts, how these operators acts on this thing. So you construct this operator. And the whole point of constructing these operators is like that, is the fact that you know how the generators L1, L-1, and L0 acts on these guys. And the way we constructed them, like the conformal invariance is completely manifest. So you can forget about all the details I told you, and you can think of them as a CFT operators at this point. And when I say CFT operators is the normal CFT operators, and the action of L0, L1, and L-1 on these operators are exactly same as the thing you read in the CFT book. So once you do this, you can start writing down 2-point correlators. So for example, you can take O and O bar. You know.
Excuse me, why didn't you take it to be the same Z coordinate on the manifold? Why do you have to invent a pseudo?
Oh no, so the point is, so this Z space has nothing to do with the actual surface, because this Z lives on a, so this Z lives on a Riemann sphere. So this Z has nothing to do with the actual surface. So you can think, so as I was saying, the analogy is that the actual surface is like field configuration. So if you change the surface, it's like you are dealing with a different CFT, but still your operators are still described by the Z variable. Like whether you're dealing with the Ising model or something else, the operator is still described by Z.
So it's an auxiliary space.
Yeah, it's an auxiliary space. Yeah, exactly. Good. And then once you have these correlators, once you have these operators, you can start constructing correlators. So, and you can use some input from the group theory. So for example, we know that if you fuse two holomorphic guys, there is no identity in the channel. So the correlator has to vanish, which is 0. If you take a holomorphic guy with the anti-holomorphic guy, we know there is identity in the channel. So it has to be proportional to this. And this functional form is fixed by the conformal invariance. So it's just exactly like how you figure out the 2-point correlator has to be this functional form. Again, you can think about the 3-point correlator. And again, the functional form is completely fixed by the conformal invariance. And there is a 3-point coefficients living here, which is denoted by FP. And so the upshot of everything is that we have 3 different descriptions of the same object. On one side, you take objects on the surface, you integrate them together and integrate over the whole manifold. So this defines your 3-point coefficients. You can go to the bigger space. Instead of forms, you can think about the functions living on the bigger space. You can multiply them together and integrate over the bigger space. That's also define your 3-point function. And finally, you can forget about all these things and you can talk about these 3 operators. And these 3 operators also define a 3-point function. And the whole point is that once you have constructed all these operators, you know how the 3-point coefficients and how their 2-point function behaves. You can forget everything about the hyperbolic manifold. And you can do an actual CFT bootstrap, because at that point you have translated your problem in the well-known problem of a CFT, like a bootstrapper would handle. So to be more concrete, as I was saying, that we construct operators labeled by the points on the Riemann sphere. So there are 3 kinds of operators depending on 3 objects living on the surface. Like the operators that live on the equator are like the operators that are connected to the functions. The operators living on the lower hemisphere is connected to the holomorphic differentials. And the operator living on the upper hemisphere is related to the anti-holomorphic differentials. So there, as I was saying, there is a 1-to-1 correspondence. And once you establish the correspondence, you do not need to think about the function surface anymore. You can think about a CFT.
There must be a conservation of misery, right? And is it really much easier than the other one? Can you convince us?
Yeah, I will convince you in a second.
Okay.
I hope so. Once you make this connection precise, the actual bootstrap problem becomes nicer because of precisely of this reason. So now you take the correlator of two holomorphic and two anti-holomorphic guys. You consider a 4-point correlator and the conformal weight is n, which is related to the holomorphic weight of the differential form. And you also know how many of them are present on the surface because you have some information about genus and everything. And then you immediately know that this can, by conformal invariance, it can be written down this way. And then just from the CFT, we know that they can be expanded in the S channel or the T channel blocks. So this information about blocks are known. So in the earlier context, this information was completely missing. So there was some hidden structure and those structure was completely missing. But here we do not have to do any hard work because we already know what are the blocks and all those informations are. So there is a clean separation between the dynamical information and the kinematics information. So these blocks are like the kinematics information, which exactly follows from the conformal symmetry. Like once you know there is a hidden conformal symmetry, you know all these contributions. And then you can focus on these objects, which are 3-point coefficients. And these coefficients actually describe your surface. If you change your surface, these coefficients will change.
Well, if I know how to compute the Casimir eigenvalues in the group theory approach, I should arrive at the same conclusion, right?
No, the point is that there are two things. First of all, it's extremely hard to actually solve Laplacian on a surface. First thing, and second thing is, suppose you have to prove a bound that among all the genus to surface has to satisfy a bound. But then there are in the genus 2 there is a moduli space. So technically there are infinite number of surfaces which are described by the same gamma. And the moduli appears because gamma fits into the actual group PSL2 or in various ways. In fact, infinite number of ways. But then you cannot go on proving like solving Laplacian equation for infinite number of cases. So you have to go through this procedure. And just another technical remark that is I told you is almost like CFT, but is slightly like easier than a CFT because in a normal CFT, what happens if you take two operators and if you cannot put them on top of each other because there is a OP singularity. But here in the S channel, because of group theory, there is no singularity. So Z equals 0 is a regular point. So even if, so the conformal block in the S channel is the usual block we use as a bootstrapper. But in the T channel, the blocks are slightly different. They are linear combination of something called block and the shadow block. But at the end of the day, I just like, if you do not know the details of the conformal bootstrap, the only thing I want to tell you is that here there is no notion of OP singularity. The OPs are regular. So it looks like somewhat like chiral ring where there is no, you can take two operators and put them on top of each other.
Is that true for any choice of gamma?
Yes. Yes. So that's an amazing fact. It's true for any choice of gamma. And once you know this, you can basically, you have S channel and a T channel, you write down a crossing equation. And at this point, it exactly becomes like the usual CFT problem. I will not go into details. And then you can put bounds basically using this thing. And can I have 5 more minutes? Then I will just show you some sample results. So as I was telling you so the idea is that the multiplicity of these operators are dictated by the Riemann rock. So once you know the genus and this list of values, then you know the multiplicity. And the idea is as long as you are dealing with the gamma where ln is greater than 0, you can set up a bootstrap problem and basically you get the strongest bound by applying it to the minimum n such that ln is greater than 0. So basically you have to, and then the idea is then by Riemann rock you can show that the minimum value of n can either be 1, 2, 3, 4 or 6. So these are the all possible values. So you can create a table and you can put some bounds. So here is the table. So if n minimum, so you can ignore this for now, this two column. So if n minimum is 1, there is a bound which is 8.4703 true. And in all cases, you can see that our bounds are very close to the largest known value, which are given by these surfaces. And this 6 is the one which is this 44.8. So this is the one that corresponds to the smallest orbifold with the smallest form. And then you can ask this following question, that if I know what is the minimum possible value of n that is allowed by a surface, what is the next minimum possible value? So you can do another kind of bootstrap where you take a mixed correlator bootstrap, where you take these two pairs, 3 and 4, 3 and 5, and put another bound. So instead of considering ON bar, here you consider ON like system of correlators which involves all possible combination of n and n prime. And again, you can see that these lambda ones are very closely saturated by known surfaces. And you can use these two tables to carve out the space of hyperbolic orbifolds in the following way. So I will give you a sample result. So for example, someone comes to you and tells you that the first eigenvalue is greater than 30.35432. And I'm claiming that once you know this information, just by using this table, you can immediately tell him or her that the surface has to be 0, 2, 3, 7. There is no other way. And how we can do it? We can do it in the following way. So if someone tells you that first eigenvalue is greater than this, then from the table you can see that it cannot be the first 4 lines, because in all these cases the value is less than 30.5432. So the only possibility is the last line. So that means this table tells you that if the first eigenvalue is greater than 30.35432, then the minimum has to be 6. So once you know the minimum has to be 6, you can use the Riemann rock to show that the second lowest has to be either 8 or 12. And now then you realize that if it is 12, then it has to be 0, 2, 3, 7. So to prove that if the first eigenvalue is greater than this, if the first eigenvalue is greater than this, then the surface is this, you only need to exclude the possibility that minimum is 6 and the second lowest is 8. So to exclude that possibility, you use the second table and you show that using 6 and 8, the bound is 23.0997, which is less than this 30.35432. So basically 6 and 8 is ruled out. So the only possibility that remains is 6 and 12. And that means the orbifold has to be 0, 2, 3, 7. So this basically tells you that like just using these tables, you can carve out the all possible space of orbifolds, which is like carving out the space of CFTs. In the same way, you can like put a bounds on the higher zeta surface by identifying that the holomorphic forms with weight 1. There are G of them on a genus G surface. So you set up a bootstrap problem where the externals are labeled by A, B, C, D, and all these labels can go from 1 to G. So this is a G cross G correlator system. And again, you can put bounds by using this. And we have this humongous table here where we listed all our bounds from genus 20. And of course, except for genus 4 and genus 6, which are two anomalous cases, in all other cases, we do better than the known bounds. And for genus 4 and genus 6, somehow the best known bound till now is by Young and Yao from 1980, which is 2 and 1.6. And somehow all efforts to improve this bound has not been successful for genus 4 and genus 6. So this line is an improvement from last year, and this line is also a paper from 1990, where they have bounds. And in all cases, you see that except for 4 and 6, our bounds are better. And for genus infinity limit, we can produce a bound, but in the genus going to infinity limit, our bound is better than the Yang-Yao bound and the bound from last year. But then there are some other analytical results which uses the fact that the genus is very large, and that result produces 0.25. So it's an open question how you can improve the bootstrap problem to actually better understand this 0.25. And I have 2 more slides. And as I was saying that, so you can actually extract something called extremal function from the linear programming. And the idea is once you plot the function, so it starts from positive, then goes negative, and then again it becomes positive. So you have a root here. So this first root gives you the bound on lambda1. And then you can look for other minimums on this function. And it turns out these other minimums are very good approximation of the low-lying eigenvalues. So for example, for the 0, 2, 3, 7, we have these values here. And then you can compute the actual values like by solving the Laplacian. And you can see that these values matches quite well: 142, 142, 201, 201, 323, 323, and 456, which is 454. So this is how you can hopefully extract the spectrum. If you're more powerful enough, you can make these numbers better and better. And the hope is maybe you can like detect chaos by actually extracting the full spectrum if you are more and more powerful.
Where did this function come from that was doing this?
So there are some details, and the details are in the devil. So the point is that here this functional comes from the actual linear programming you do. So the idea is that when you do the bootstrap, the job of the computer is to give you a functional. So you propose a spectrum, and then the computer finds you a functional. If the computer finds you a functional, then you know that proposed spectrum is wrong, and that puts a bound. So this functional comes from the computer basically, and this is how you prove the bounds using this functional. Because so the idea is the computer will give you a function. The first root will always give you the bound, and this is this 44.88835. And the higher roots or the higher minimums will be a good approximation of the actual spectrum.
When you say the first root gives you the boundary, but the
first root is the first one that crosses from the negative side.
Okay.
And you can also so there's a hope that one might be able to actually analytically find these extremal functionals. So in the math literature, for example, in sphere packing, this kind of functionals has been actually written down explicitly by Vyazovsky. We solved the 8-dimensional and the 24-dimensional sphere packing problem. And finally, we have some future directions where you can talk about like mixed correlator bootstraps. You can talk about other groups. You can talk about higher dimensional manifolds. You can talk about non-orientable surface. So there are various things to explore in future, and each of them are like very exciting because those will produce new results for mathematicians also. And finally, there is a connection with de-Sitter bootstrap. So people who are thinking about de-Sitter also will find it useful. That's it. Thank you.
I still was curious to understand what the normalization here was. Did you say it was for some canonical choice of the curvature?
Yeah.
Like what?
Oh, so you basically assume the sectional curvature of the hyperbolic surface is -1.
Ah, okay.
Yeah, because otherwise the numbers don't mean anything.
Yeah, right. That's what I was trying to get at. I see. So curvature -1.
Yeah. The sectional curvature is -1.
Yeah, can you say a few words about de-Sitter bootstrap? I mean, are there any new results on that about cosmological correlation functions and everything?
Yeah, so this is a very recent thing. So in like a couple of months back, the EPFL Lawson group wrote a paper where their EPFL Lawson, led by Joao and other people, and their idea is that in the de-Sitter, the late time slice, the correlator should satisfy the SO1, D symmetry. So you can try to bootstrap using this SO1, D symmetry, but these are in very baby stage. Like I guess the only connection at this point is that the same group appears. The crossing equations we write down is also applicable in those scenarios, but it's not clear what are the physics wise. I guess the de-Sitter is a bit murky. Like it's not clear what are the interpretation of OP coefficients and whatnot. things to explore over there also. Yeah, but all I mean to say that the equations we write down is also true over there. But the meaning of OP coefficients, meaning of spectrum, these are not very clear. Thank you.
After you calculate the eigenvalue, how do you go back to the signature? How do you find the signature of the gamma?
No, you don't find the signature of the gamma. So the point is that, so here's the thing. So you have some, so you give in that in as an information. So suppose you want to put a bound on genus to surface. You know that your gamma, the first entry of gamma has to be 2. And all the other entries has to be 0, 0, 0. And that also tells you that, like, for example, that tells you the dimension 1 holomorphic forms a vector space with a genus G surface with a dimension G. So you know there are G of them. So you set up a bootstrap problem with G operators and you get some bounds. And then you say these bounds are applicable to all the genus G surfaces. So it's a unidirectional flow.
Each time you want to put a new bound, you assign a different gamma and then.
Yeah, each time. So every information goes, so the information goes in here. So in this external, you have this thing. And then you have some control how many operators you put in here. Like in what's like, and that number is dictated. So this number ln is dictated by this Riemann rock, and you can see there is a G and there is a Ki. And once you know the gamma, you basically have the list of G and Ki's that determines your ln. That determines how many things will be there over there, and that will produce a bound.
Can you say something about OPE coefficients, like in this case?
Yeah, so here I guess the point is the OP coefficients. So here also you can define OP coefficients, and the OP coefficients are related to the on the manifold level. It's related to taking 3 functions, multiply them together, and then integrating over the whole manifold, and that produces a number. And the idea is that either you can think from the surface level that produces a number, or you can go to this bigger space, which is the group manifold, slashed out by gamma. Again, you can multiply 3 functions and produce a number, it's the same number. Or you can think of like, consider the 3-point correlator of this kind of operators, and that will also produce a number. And we showed that all these 3 numbers are same. And once you can express in this number of operators, then you have the usual CFT language. And the only difference is there is no OP singularity. So you can put 2 operators on top of each other in this case.
Does that gain you any mileage or any?
Yeah, that gains some mileage. So in the sense, some technical mileage. For example, in the usual CFT, you basically write down a crossing equation and then expand around z equals half, because z equals 0 is a bad point.
Right.
But here you can do around z equals 0, and that makes life simple. So there are some like technical advantage. In fact, I think the fact that in the usual CFT, people have worked for years after years to get the island in the Ising model, because there are struggles with the z equals 0 point and we have to expand around z equals half. But the fact here we are getting such a nice, almost saturating bounds has to do with the fact things are nice and you can expand around z equals 0. And there are also other nice facts. For example, if you take this h function, this function t and expand it, all the coefficients that appear, they are actually polynomials of delta. So you can explicitly write them out. So things are very nice. And also there is in the combinatorial geometry, there is something called polytopes. This H delta case also forms nice polytopes. So there is a connection with combinatorial geometry also. So things are very nice over here. And they share a lot of features with the CFT, and that's why it's exciting also from our perspective, safety perspective.
Chris, do you want to ask if someone?
Oh, yeah. Anyone online?